So Caitlin Howell is an associate professor of bioengineering at the University of Maine. She completed her BS and MS degrees in biology at the University of Maine, and then a PhD in physical chemistry at the University of Heidelberg in Germany. She returned to the US for postdoctoral work at the Weiss Institute for Biologically Inspired Engineering at Harvard University, where she developed a passion for looking at natural solutions to develop cutting-edge technologies and then translating those technologies to the market. Caitlin said, "See you later, Harvard," and rejoined UMaine as a faculty member in the Department of Chemical and Biomedical Engineering. They're still gnashing their teeth over that one. Since then, she and her team have worked on drawing inspiration from nature and working across the disciplines of biology, chemistry, and materials science to address major issues in human and environmental health. She's been recognized with numerous awards, including most recently a 2023 Gilbert Lectureship from the National Academies of Engineering. Beating a dead horse here, also a big deal, just pointing that out. Okay, and I'm just going to read this directly from your email because I felt that I'm with you on this one. Okay, I was totally feeling this. Favorite science theme, popular culture. This is hard. I got that one.
Oh, yeah.
I'm a huge sci-fi nerd, but I think I'd have to go with Star Trek: The Next Generation. Gets better. I want to be the one to invent all the biotechnology they use, but using sustainable materials, of course, because it all has to be broken back down for reuse in the replicators.
Right? Right!
And Caitlin's talk title is Maine's Secret Superpower, Environmental Sustainability Beyond Packaging.
Yes. So I'm assuming this thing is on. You can hear me okay? All right, and I didn't even bother to put the title up there, right? This is the last talk. We're just going for it. Whenever you're ready, let's hit it. All right, do we like this picture? No, we do not. I think we can all agree that this is really, really bad, and we know that because we're starting to hear about other effects like microplastics and PFAS. We don't like this. As you heard, in my lab at the University of Maine, we do bio-inspired engineering, which is a fancy way of saying we look at nature for the way that nature solves problems, and then we steal those ideas, and we use them for human problems. Yeah, all right, so let's do a little bio-inspired engineering here. Do we like this? Yeah, all right, this is a lot better. We agree. The crowd has spoken. It's not that there isn't anything happening in here, though, right? Like in the previous picture, there's evidence of stuff being produced, stuff being consumed, but there's a major difference here. There is an awesome recycling system at work here, right? All right, so if we're going to steal these ideas and use them for human problems, well, maybe here we don't actually want to steal anything. Maybe we actually just want to sort of insert ourselves into this amazing process that already exists. Can anyone think of a state that maybe has a lot of experience with making human use things out of materials like this? Maine? Oh my goodness, what a great coincidence that we're all already here. Fantastic, all right. And so you have probably already seen that actually we're getting a lot more natural materials in the packages that we have. The revolution is coming. But I'm here to tell you that we can actually do more. And it starts here. Did you know that down in the southern part of this state, in Westbrook, Maine, there's a paper company called Sappi, and they do this stuff. So what this actually is a pattern on the surface of paper. And they make this by the megaton, right? They make tons of this stuff. They're a paper company after all. All right, why in the heck would you want this? Well, they sell their product to textile companies generally who take that pattern, whatever pattern they want, they can make anything, they press it up against the material that they want, and when they pull it away, they have that pattern on a material. They can use this then to make cool things like handbags and shoes. People, handbags and shoes, what are we doing here? So when we learned this, we went, no, we can do a lot better than this. We took this into the lab and my video's a little squished in sideways, we put liquids into this thing. This thing was controlling liquids on very, very, very small, precise scales using stuff that's made to make shoes. Why do we care? Where can we use this? Raise your hand if you felt like you threw away over 100 COVID tests in the past 30 years. Yeah, right, okay. And the thing is, though, those are really useful. They're controlling liquids, right? And the more we control these liquids, the fancier we can get in terms of diagnostics. So we said, hey, paper company, can you make us some channels that can maybe intentionally control liquids? Turns out they can really easily. These were some systems we designed to just mix two liquids together. And when we did it on the paper company stuff, we actually couldn't tell the difference between what the paper company made and what was made using traditional plastics and glass and other things that we can't recycle. Cool, huh? We can do this. Here in Maine, we can do this, but it gets better. Check that out. What you're looking at is a material that they make with a pattern on the surface that is on the scale of the wavelength of light. It is so amazing that when white light hits it, it breaks out into its component colors. And people, they're making this by the ton and using it for shoes. We said, wait a minute, no. We know where this could be useful, lots of different areas, but my favorite at the moment is actually in a type of sensor. So we have a deep need to understand the world around us, lots of things, including water, right? What's in our water? We need to know. So we took this material and we put it in the lab, and here on this side, you're looking at what it looks like looking through clean water, that diffracted pattern. And here, when we put a contaminant in this water, we can see the difference using Maine paper technology. So, what I want you to walk away with from this talk is that Maine has an incredible superpower, and one that the world really, really needs right now. Here in this state, we have the research capacity and the manufacturing capacity to be able to do amazing things with natural, renewable materials. And if we think a little bit outside the box, or outside the package, if you will, I think that we can actually start to apply these materials in a lot of different places, in a lot of different ways, and make a sustainable future for everyone.
You're not going to make me be the sole person talking. Okay, thank you.
Mine's just a quick one. I'm curious, what's the IP behind this? Is this actually something that SAPI owns, or what's the manufacturing process behind this and everything else?
That is a great question. Okay, so the IP behind it is actually, so I told you that their customers are the one who, they buy this material and they use it to make patterns on stuff. They will actually, own the pattern. But SAPI actually has this incredible technology where they have a gigantic electron beam that they use to be able to make their stuff. So that's where their IP lies. But yeah, when we come in and we're like, hey, we want this custom texture, then we work directly with them. So the IP is actually something we can figure out. But that's a great question.
IP is intellectual property.
Yes.
Just in case. Yep.
Thank you.
So
Interpreter.
Yep.
So on the sensor, does it have the capability to determine what the contaminant is and not just that the water's contaminated?
Yes, and I'm so happy you asked that question. I didn't have time to get into it in 5 minutes, but the really cool thing is that those different wavelengths of light, they can actually be useful, and they're used in normal water quality testing. What happens when you have a contaminant in water, oftentimes it will absorb some colors and not others. And this is true when you get into the UV region as well, right? So by looking at what colors are absorbing and what colors aren't, including in the UV region, we can get a lot of information from that. Information that usually comes from very expensive pieces of equipment called spectrometers. So yeah, we can start to tell what's in it too.
Excellent, thank you.
Mm-hmm.
I was wondering for the, oh, sorry.
No, go ahead.
No, it's you.
For the liquid or the fluid contraption, how sterile, or how do you sterilize something like that?
Mm-hmm. So it's actually made to be pressed up against nasty chemical polymers that are what are coating those materials. So it's actually really chemically resistant. We just drop it in ethanol. Yeah.
That's awesome.
There's a lot of that in Maine too, so we should be good.
All right.
Right? Ethanol with the beer.
Yeah, beer. I think we should test after this. Right?
I'm with you.
Yeah. All right. Cool.
Can you tell us more about how your research relates to studying PFAS in Maine?
Oh, my research does not relate to studying PFAS in Maine yet. That is a terrible, terrible problem. But I, probably like all of you, are really cheering on those scientists who study PFAS and are figuring out ways to solve it. And I'm there with you, community, but I don't do that in my science.
So do you have a favorite bioengineered thing that you've done? Like where you've been inspired by a particular nature thing?
I get inspired by things every week, and every week is my new favorite thing that I test. So that's the fun thing about being a scientist. You're like, ooh, what's that? Let's go check that out. It's great. So I can't say I have a favorite. I like all of this, but I really do like this right now. Because just the potential, yeah, there we go. The potential impact, right? That's why I was so excited to be able to come here and share all of this with you. Because who knew that that thing existed in our state? I mean, what else is there that we could use? So, yeah.
All right, I think
We ready for it?
Caitlin and I should go test the ethanol.
Let's do it.
I think we're good, thank you.
All right, thank you.